Continuing where I left off, so we're talking about what they're made of. So an alpha particle, one is a particle, you must remember that. It's made of 2 protons and 2 neutrons, and that's equivalent to a helium nucleus. Now, it's not a helium atom. A helium atom will have electrons orbiting around the outside, but it is equivalent to a helium nucleus. If I were to kind of draw it, 2 protons, let's say those are the protons, and 2 neutrons. That's what it would look like. So don't forget that. A beta then, again, a particle, very important. Very, very important. And it's a fast moving electron. Now, the very beady-eyed or beady-brained perhaps of you might say, hold on, we're talking about nuclear radiation, so something's coming from the nucleus. How could we possibly have an electron being emitted from the nucleus when there are no electrons in the nucleus? For those of you that are wondering that, this is basically what happens. If you remember that the relative charge of a proton is +1, an electron -1, and a neutron is 0. You'll need that to understand what happens. So if my nucleus is containing protons and neutrons, what can happen, let's just do an example. Let's say, can you see? Yeah, I think you can see this. Everything with a P in is a proton, so 3 protons and 3 neutrons, everything with an N in. One of these neutrons, because it has a relative charge of 0, it can actually turn into 1 proton and, 1 electron. I have to draw it tiny because just to kind of show that it's a completely different size. Because if I have the charge of that neutron is 0, the net charge will still be 0 if it changes into a proton electron, because the +1 will cancel out with a -1. Now the proton will now stay in the nucleus. The new proton is no longer a neutron, so that's turned into a proton, and the electron is fired from the nucleus, as you can see. So that's kind of what happens. That's a little bit more complicated, but in case you are wondering how that happened, how we've got an electron being emitted from the nucleus, well, that's the reason why. So fast moving electron, and finally gamma is not a particle. Okay, so it's not a particle. We would say it's an electromagnetic wave. You can also write EM in capitals, wave. So you would be expected to remember that. Of course, I have left myself with no space, completely rookie error. So the next thing I would want to talk about is how far they travel in air. So let's put distance. Travelled in air. And let's just continue on with this. Alpha particle, that can't travel very far in air. It's quite big compared to the other two. Well, gamma obviously is a wave, but if you imagine 2 protons and 2 neutrons together is bigger than 1 electron. Quite a big difference, in fact. And so it's quite hard for it to go very far. So in air, we would say a few centimeters before it's stopped. Okay, then a beta particle, so my fast-moving electron, a few meters before it will be stopped. It's very, very small and it's fast-moving. Gamma radiation travels many, many meters. Oh, I put a few centimeters here. I meant to put meters. Whoops. Okay, whoops. Many, many meters. I shouldn't really put an apostrophe there. That's bad English. Okay, so that's how far they would travel in air, and we're not doing anything to attempt to stop it. The next column, which I'll have to there we go, add on there, is going to be, let's just move that along a bit, something that I wish massively that I could show you in person. There's a really good demonstration I can do using actual radioactive sources that we have in the science department. For obvious reasons, I can't show you that, so you have to well, I mean, you have to partially take my word for it, but also I would hope that you would go and look on YouTube or the internet for some videos of it happening, because there's undoubtedly many videos out there of the demonstration that I would do. And the demonstration basically shows you what I could use to stop each of the 3 types of nuclear radiation. Obviously, we've already talked about how much air would stop it, but now what actual materials could I use to stop it? So let's just carry it on here. Let's just mark the end of the paper like that. So this next column is what will stop it. Alpha radiation is stopped by a sheet of paper. But yes, a sheet of paper stops it. Does that mean a bit of metal won't stop it because it's paper that is needed to stop it? No. Obviously, if paper can stop it, then something thicker than paper can also stop it, okay? So what will stop it? A sheet of paper and anything thicker. So I might actually put that in, and anything thicker. What will stop beta radiation? Beta radiation is stopped by a thin sheet of aluminium plus anything thicker. Will I fit that in? Oh, I'm gonna have to squeeze it in. And what will stop gamma radiation? That's very difficult to stop. Gamma radiation would be stopped by very thick lead. Okay, so very thick lead, or many meters of concrete. But really it's quite hard to stop gamma radiation. What else do I want you to know about these types of radiation? I suppose I'd like you to know what uses they have. So alpha radiation is used in smoke detectors. In the detector, inside the actual smoke detector, there is a detector that picks up alpha radiation. So there's also a source of alpha radiation in the detector, and it wants to be picking up that those alpha particles. If the smoke gets in there, and starts blocking any alpha particles, or it ionizes them, then that detector will pick it up, sound the alarm to tell you that there is a fire. Okay, so really good use. The most common use is in smoke detectors. Beta radiation is used for paper milling. So basically measuring the thickness of paper. Again, there would normally be so this could, let's say this is the detector. This is emitting, i.e. giving out beta radiation. And again, my detector is picking up that beta radiation. Once some paper's been made, it goes through in between the source of beta radiation and the detector, and it's going to stop some of that beta radiation, and depending on how much radiation that detector is picking up tells you how thick that paper is. The less radiation it picks up, the thicker the paper must be, because it's blocking more of that beta radiation. So that's how paper milling works. Gamma radiation, I can think of a lot more uses of that. The most obvious one is that we use it to treat cancer patients. Even though gamma radiation can cause cancer or increase your risk of cancer, we also use it to destroy cancer as well. If you target it at the tumour, then you can actually kill the cancerous cells. If you've already got cancer, then you don't really need to worry too much about gamma radiation giving you cancer, because you're using it to cure you from it, not, you've already got the cancer that you would be worried about. And what else? We use it to sterilize hospital equipment, and we use it to detect leaks and blockages in pipes. So I suppose I could draw another diagram for this one. So you've got people standing up here on the top. You've got pipes underneath. So this is my pipe going underneath. Now you can't use alpha or beta radiation for this purpose, because this is all concrete, and nothing will get through the concrete except gamma radiation. So what will happen is they will have a detector above the surface. Let's say there's a blockage here. I don't know what the blockage is, but there's I don't know, massive rock. I'm just completely making this up. Blockage here. You put a source of gamma radiation, so something that emits gamma radiation, into the water supply, or so that it goes along. Here we go, it's travelling along, then it stops here. So this detector can pick up gamma radiation all the way along here, all the way along here to here, but then as soon as you put the detector over here, it no longer picks up that gamma radiation from below the surface, which means it has been stopped further on. So the last point that detector picks up the gamma radiation, that suggests the blockage is just underneath there. So at the moment, that's all I can think of. I think we use it for food transport of food, and as well, like killing off bacteria and things, but don't quote me on that one. So that's, I think that's what I want you to know at the moment in terms of alpha, beta and gamma radiation. But I do actually want to draw you a diagram which they like to use in exams. Basically, it will look something like this is the detector. This is my source of radiation. And I mean, it could be slightly different to what I'm drawing. Sometimes they do it in a different order. Paper. Aluminium. I should put one more, shouldn't I? Doesn't matter too much how straight this is. I just want you to have recognize. Can you actually? I don't know how much you can see. This is going to be thick lead. That word is also lead, but not in this case. It's thick lead. So let's say it's giving out 3 types of radiation: alpha, beta, and gamma. So we know that all 3 will manage to get through the air until we get to the paper. The paper will block off one of them. That will tell me that this one is alpha radiation. So if I put the detector, let's say I place this detector over here, then I know that the only 2 that got through would be beta and gamma, so I know that one would be alpha. Then when we get to the aluminium, then you've got beta radiation being stopped. So then I know that one there is beta. So again, I'll have to make sure I put my detector in here. And I know that last one will be gamma. I suppose the thick lead's not really needed because we know it must be gamma. But just to check, put some thick lead in there, stops the gamma radiation. So there we go. So you may see a diagram very similar to that in your test paper. They do like to do that.